stranger keep you tune. Tell me, is a stranger young?
This is going to be an example of duality, or more specifically, it's going to be an exercise in deriving a current source. Here is associated voltage source. This right here, this common emitter amplifier. This common emitter amplifier, as you can see, has no component values. Component values are not needed at this point in deriving a current, its associated current source. So that's what this little exercise is going to be about. First of all, before I get started, there's some things to know or things to remember. Number one, E, S, subscript S, is a more generic term than VS. If you're asked to draw a voltage source, if somebody says, draw me a voltage source, well, you don't know if that's AC or DC. They don't stipulate. So you can use the general expression or the general term E. V is more specific. So in books, you're going to see, there's sometimes when you see E and sometimes you see V, VS or ES. Well, or V subscript, whatever, 1, V2, E1. V is more specific, relates to DC, whereas E is general, it can relates to either DC or AC. So you see that from time to time in various books. Another thing, this for every, say for example, series circuit, there is a parallel circuit. That's called a duality. And here's a few examples of a duality. Right here. Here's a series circuit, parallel circuit. That's a duality. Voltage, current is, the duality of a voltage is current. The duality of an open circuit is a short circuit, and on and on and on. You have matter, antimatter. You might have gravity and anti-gravity, black holes and white holes, etc. and so forth, yin and yang. So for every idea of one, like a node, the duality of a node would be a loop. The duality of an open circuit would be a short circuit. But the ticket item here, the big idea in this particular case, is the voltage source and current source. Everybody knows about capacitors and inductors. One's a duality of the other. Resistors and conductors. Those are dualities. There are many, many, many dualities in life. And here are a list of a few. And it's just the same way in terms of voltage source and current source. Here's a voltage source. Now, one thing of interest in this voltage source, this would be, these two nodes, outputs, would be the equivalent of the output of a power supply. This resistor is not part of any circuit external to this power supply. It's part of the internal resistance of the power supply. Okay, so you don't see this resistor, but power supplies like or voltage sources like current sources have an internal amount of resistance or conductance associated with them. And so you have to show that. So in this particular case, the voltage source is 10 volts. It has a internal resistance of 4 ohms. So how do you determine its associated current source? You short circuit this thing out temporarily, and then through Ohm's law, you take 10 volts divided by 4 ohms, you get 2.5 amps. So here is the duality of the voltage source, i.e. the current source. So that's how you derive at 2.5 amps. How do you get 0.25 mhos? Remember, mhos is the inverse of ohms. It's spelled in reverse and is pronounced in reverse. And you use the reverse ohmic symbol. You just simply take 4 ohms and divide it into 1. And that gives you 0.25 mhos. And so mhos, or conduct, and that's conductance. This should be GS. This is a GS. Okay? And GS is the duality of RS. Here is RS, the source resistance, and here is GS. Now, as you can see, This resistor is in parallel, which makes sense because it's the duality of a resistor in series. So that's why you would put the conductance in parallel with the current source. The current source is a duality of the voltage source, or a voltage source. This resistor is in series, so thus this resistor is in parallel. So the equivalent current source for this voltage source is this. A current of 2.5 amps at 0.25 mhos. Here is another example where you have 2 amps of current source and 0.143 mhos. Okay, so how do you convert one to the other? Well, you take the current source and divide that into 2 amps, 0.143 mhos, and you get 14 volts. So that's how you get that current source, voltage source. So this would be the equivalent voltage source of this current source. So if you had a current source of 2 amps and a conductance of 0.143 mhos, then the equivalent voltage source would be like a power supply with 14 volts with an internal resistance of 7 ohms. And one last thing before I get going on this, something you have to know. Everybody knows that when you have 2 parallel resistors, or 2 resistors in parallel, and you know what the voltage up here is, it's easy to determine what the current is through each given branch. You just take the voltage and divide it by the resistance, and you get the current through that branch. So, for example, if you want to know the current through R1, you take this voltage divided by R1, you get that current. But what if you don't know the voltage? What if you only know the current flow into this parallel branch? Well, then the formula for that, and there's a reason for doing all this, the formula is you take the currents going into this branch, you multiply it by R2 divided by the total branch, which is R1 plus R2, and that gives you the current in the opposite branch. So R2 divided by R1 plus R2 times the current gives you the current through R1, and vice versa, as I have here. The current through this branch is equal to R1 divided by R1 plus R2 times the current source, and that gives you the current through this branch. Now, why am I saying all that? Well, because when you have a situation like this, here's a current source, and like all power supplies or all current sources, they all have loads. You have to have a load, and you have to be able to account for that load. So in order to account for the load, you have to determine the output voltage or the current or the load resistance, in this case the conductance resistance or inductive or conductive resistance, and the resistance through this branch is equal to the conductant load divided by the total source conductance plus the load conductance multiplied by this source current, and that gives you the load current. And once you know the load current, then you can find a load voltage. And the same is true with a normal voltage source. Here is a load, let's say, that's attached to some power supply. That power supply is going to have some internal resistance. Now, it may be low, it may be high, but whatever it is, here you take the load resistor and divide it by the total resistance, and you multiply by this voltage, it gives you the voltage load. And one last thing before I get going. AC, when you say AC as opposed to DC, a sawtooth is AC. Okay? It's not just a sine wave. When people think of AC, they think of a sine wave. No. Sine wave is just one of many AC signals. A square wave is AC. It's made up of a lot of small sine waves. So everything is made up of small sine waves. Everything here, a sawtooth, a triangle, a ringing, overshoot, pulse width modulation, on and on and on. There's dozens of examples of what AC is. There's only one example that I know of. It's an example of a DC, and that's just straight on DC. So if something's not a straight DC, then it's all AC. Okay, so all these that you see here, they're all examples of AC signals. That's another important aspect. And So remembering dualities, remembering the voltage divider formula, and the fact that all these are AC signals is all important in determining. The ultimate question here is, in this particular example, is how to find the equivalent current source of this particular common emitter amplifier, and then draw it. What does the current source look like for this common emitter amplifier, or the duality of this? Now, as you can see, there are no component values. At this point, no component values are needed. The only thing that's important in this circuit that you need to know is the input current is 10 microamps per RMS in this example, and under varying load conditions, what's the output current? Well, in this particular example, when the load is 1K, the output current is going to be 490 microamps, and when it's 5K, it's 455 microamps. So there's two conditions, and you need that delta, or that difference between the two. So when you have the difference, what you do, first thing we need to find is the conductance of this circuit. Okay? So if the question is, what is the conductance of this circuit, so that we can eventually draw the duality of this circuit, or its equivalent current source. Right now, this is a voltage source. We want to draw the equivalent of its current source. So you need to find the difference between varying loads. And here is what we're given, or here's what is given. And then you take the individual current, multiply it by its resistor, and in one case you get 0.49 volts, and in another case you get 2.28 volts. So we've got both elements needed. We've got a difference in current, which is right here, 35 microamps. 35 microamps is found by subtracting 455 microamps from 490 microamps. You get 35 microamps. So that's a delta of 35 microamps. And the same thing with the voltage. It's a difference of, well, 2.28 volts, subtracting that from that 0.49 volts, and you get a delta of a differential of 1.79 volts. Here's the formula. You take the difference in the current, divide that by the difference in the voltage, and here you go. Once you know it, it's very simple. Here is the duality of the resistance, which is called conductance, and it's in mhos, as you can see. Mho is equal to MHO and S, mhos. Mhos is the duality of resistance. It's just the resistance inverted, that's all. So we're on the way of finding out the equivalent of this voltage source, the common emitter amplifier used as a voltage source. Wait, what is the equivalent, or the duality of this, the equivalent current source? Now that we found the conductance, which is right here, 19.6 micromhos, okay, so now what do? You take that micromho and you multiply it by the individual output voltages. In this case, you multiply it by 0.49 volts, right, because that was one of the values, and you get 9.6 microamps. And the second value is you multiply it by 2.28 volts, and you get 44.7 microamps. Now, in each particular case, if you add the current that you found in the first case by the initial 490 microamps, you get 500 microamps. And you get 500 microamps in both cases. So 500 microamps is is the result of the current, the source current output. Okay, 500 microamps. Now that we found the source current, we draw the equivalent current source. The equivalent current source is right here. Here's the current source, here's the 500 microamps, and here is the conductance, which is 19.6 micromhos. And here is the equivalent voltage source from this equivalent current source. Here's the duality of this, and this is the duality of that. So it's kind of interesting to note that this circuit right here is the equivalent of having a power supply, okay, that has an internal resistance of 51 k ohms. It's kind of a neat way of looking at a circuit and saying, oh, what's the equivalent? If you had a circuit like this, a common emitter amplifier, what would be the equivalent of having a power supply that would be equivalent to that? Now we know. The equivalent would be having a source voltage power supply with an internal resistance of 51 k ohms and a source voltage, I should write that down, of 25.5 volts. So that's essentially how you find the equivalent or the duality of a circuit like this. It's duality, current source, in its most simplistic form, and then you can convert that to the duality of a simple voltage source. So here's the voltage source, here's its current source, and here's its duality here. So that's essentially it. So this was sort of an exercise in dualities. Okay, thanks for listening.